So I'll just sort of first body poll. How many of you are sort of U.S. citizens? Like where you grew up? So 2, 3 of you, 4, 5 of you. How many of you grew up in, let's say, the West Coast? How many of you grew up in Midwest area? A couple of you. East Coast? Any East Coasters? South U.S.? Okay, how about in Europe? Who grew up in Europe? 1, 2. I missed South America. Any South America? Great. Where? Chile. Very good. How about Asia, Eurasia? Quite a few. Excellent. Very good. And Australia? What am I missing here? Africa. Anyone from Africa? Good. So people from all over. A little bit about myself. Well, I'll ask a few more questions. How many of you are engineers? So hopefully we're in the EECS department. There's quite a few of you. Related science fields? And then how about, what am I missing? Am I missing what? Art, excellent. No, that's a very good one. Very good. So it's a pretty heavy focused technical audience here, which is good. But I think everyone who, art especially, right? I spent, last week I got this really cool keyboard that has 5 dimensions of touch and this sort of really plastic, silicon feel. And all of that is enabled through the microelectronics and the processing. You can play instruments that sound like a real cello or a real horn. It's really pretty impressive. And we all carry around these little supercomputers in our pockets, right? 30 processors in these phones, and the processing power of this particular iPhone is better than my MacBook Pro. Not this one, this is new, but it's really impressive what that technology is having to offer, and I think into the future it's going to be even more important that we have that real enhanced capabilities that these devices have. Just a little bit about myself. I grew up in Michigan, kind of in the middle of nowhere, up in northern Michigan. You can do 2 hands here. South of Traverse City. On a small farm, a cherry farm actually, and I was one of 35 people graduating class. Classic kind of overachiever. I had to go to a different school to take physics, and I was lucky and got into Michigan and decided to take the hardest thing I thought I could take, which was engineering physics curriculum, and was really lucky to have that here. It was hosted by LS&A and the nuclear engineering department, and really enjoyed that because I could take biomedical and nuclear and physics and engineering and all those together. Really enjoyed that. And I did 4 years of undergraduate research in high energy spin physics. Turns out DTRA, the Defense Threat Reduction Agency, was funding. This was after the Soviet Union had collapsed. And there were a lot of very smart Russian scientists that knew how to make nuclear weapons, and they thought that they would employ them, not making nuclear weapons for other people, but for doing high energy spin physics. So we were able to do collaborative research for 5 years. I actually went 1 year over my senior year here. I spent a summer, or part of a semester in south of Moscow in Protbino in a particle accelerator experiment. And I submitted my signal processing homework, my math homework. I think I was the first person who had submitted over the internet. I used LaTeX and read all my equations and submitted my, from Cyrillic keyboards over there in Russia. So I had to translate every single key from Polish keyboard over to here. So it was a really fun experience. And then turns out I was helping to develop very high-frequency resonant cavities for this physics experiment, and there are only a few experts in the world that had the modeling software to do that. Fermilab in Chicago and other places, but it turns out Michigan, University of Michigan, and I was asking around, and then Gabriel Rebez was a professor in electromagnetics, and it turns out that he invited me to become a graduate student. So I did a master's and PhD in electromagnetics. radio frequency MEMS devices, and it was a sort of beginning of that field, so it was really fun to do that work. And so I'm really grateful for University of Michigan, and I think at the time, at least in electromagnetics, we were unrivaled, right? Really very, very strong, and I think still really, really strong in that area, but now a lot of our digital and analog signal processing and design is really strong and leading. So I'm really glad to be able to come back and talk about microelectronics to a place like this. After doing all of that, getting the specialized degrees, I still felt that I really couldn't do anything. Like I could do a lot of things, but I didn't feel really competent, surprisingly. So I had a bunch of offers. I could go to full up industry and be on that tape out cycle of every 3 months cranking out new chips. I could go to academia, and I knew how much work your professors do to keep things going here, and it's a lot. I found a really great common ground, which is MIT Lincoln Laboratory. It's a federally funded research development center, and sponsored, MIT runs it for the federal government. It's about 3,000 people, 1,200 PhDs, does about $1 billion worth of research every year. So it's a great place, really at the leading edge of technology. And so I chose that, and it was a really, really good place for me to be. I started in a group that ran a clean room, a fabrication clean room. We started at 6-inch and 150 millimeter and transitioned to 200 millimeter, changing all those tool sets and processes, and went from 180 nanometers down to 90 nanometers. So how the modern chipsets now, what is the process node that is typically used? Who wants to offer the feature size of modern chipsets, let's say in this phone? 14 nanometers? 7? Okay, so you all know what that means for people who are in art. Yeah, you know the width of a human hair. Oh, you're an engineer. Okay, sorry, you're an engineer. But so we're talking 1,000 times smaller than a typical human hair. Very, very fine feature sizes. We were able to do that transition from 180 to 90, and then changing in tool sizes while continuing to process wafers the whole time over about a 1.5 year process. So that was kind of a remarkable thing to be able to, it's like changing the wheels on your car as you're going down the freeway. And then going from the technology areas and developing 3D integrated circuits and advanced readout integrated circuits and flexible neural implants and things like that for biomedical, I went to the ISR division, the Intelligence, Surveillance, and Reconnaissance division, and that's where I was in the embedded and open systems group. And what that means is you have an algorithm. I want to do a correlation or signal processing, or I want to do some radar beamforming or some signal intelligence. How do I take all that computation and put it into something that's embedded and really efficient and really powerful? I need to do 1 trillion operations per second. How do I get that? So you guys should know this. Like, what's the typical average throughput for a CPU in terms of operations per second per watt? Anyone? Typically, it's about 1 billion operations per second per watt, computational efficiency. Peak, about 10 billion operations per second per watt. A lot of things require more like 1 trillion operations per second per watt. So you can't use a CPU in order to do those computations. You need to do custom ASICs. I think the Google Pixel phone, anyone have a Google phone? It has a little ASIC just for the camera, and it does 2 trillion operations per second. Taking a picture, doing face tracking and all that. So without those custom ASICs, you couldn't do those functions. So that group, what we're doing is trying to find ways to take algorithms and implement them in embedded systems that looked at big frequency spectrums or did LiDAR and LADAR processing. And after that, helping DARPA and others create a number of programs like the DARPA CHIPS and DAHI and other these integration programs. The Office of Secretary of Defense needed someone to run a pretty big program, about a $600 million program called Trust and Assured Microelectronics. How do we have confidence in our electronic systems? And so I agreed to come help them. And in doing that, in helping them recognize that there's a bigger problem. And the bigger problem is that the department is not really making advanced circuits, aren't making those things that are 10,000 or 100,000 times more efficient than what you can get with just a CPU or an FPGA. And that's a real problem. And we aren't innovating as quickly as we should. So I was able to create a fairly large initiative. I asked for $6 billion, but I got about $3.5 billion to do microelectronics innovation for national security and economic competitiveness. And it was part of a sort of a White House initiative. Well, I helped them formulate the strategy and made it into the national security strategy and the department's strategy as well. So it was really kind of a fortuitous and lucky circumstance to be in. So that's what I'm going to be talking about today. So if you look at this, this is what we feel that the future defense systems will need. And as you're going into a location, let's say, if you're a squad of soldiers, you'd like to be able to communicate and cooperate and operate together, but you'd also like to understand what is the signaling and the Facebook and Twitter posts and everything else that's happening around you. Right now, it takes about a week to analyze all that data in order to do like a special ops mission. And by then, many things have changed. So wouldn't it be nice in real time to really understand what's happening around you, not just to perform offensive operations, but to influence the populace, to try to understand what's happening around you. That type of processing, the graph analytics, the really complicated real-time processing requires very specialized computation. Graph analytics computations, typically like the Cray XMT and the IBM Blue Gene, you've heard the Watson, right? Those processing, there are thousands of CPUs connected together. About every 10,000 clock cycles, they actually do a computation. So they wait around 10,000 clock cycles and actually compute. So that's really inefficient. And that's because they're waiting to take data from many, many sources and bring them together to do a computation. So graph analytics computations in current computation is really inefficient. So we need about a 10,000 times performance improvement for those types of graph analytic problems. And graph analytics is also really important for things like object and face detection and SLAM, simultaneous localization and mapping. So if you see those robots that can walk around and you see a sort of a cloud picture of the environment being mapped out, those are all processes that require elements of subgraph matching and pattern matching. So we're going to need big improvements in cyber and social. We also are going to have systems of systems. So in order to communicate and operate together, especially in the way that humans do, we've got our brain stem, we've got our eyes and our neurons. They call that level 0. Basically, you've got sensors and connections. Level 1 of our intelligence and our processing is taking that visual data, and in the back of your head, it starts to do localization and mapping. It says, I'm here. Other things are there, and then eventually you go to level 2, which is that's a desk, that's a friend, that's a foe, that's a person. Level 3 is threat and activity detection. So I'm seeing things move, or that's a snake, or that's a pattern. And then as you move up in the semantic chain, your prefrontal cortex starts to do all this amazing simulation about, like, if I do this, they're going to do this, and this is the functions we want to have. They should know this before we move. We've got to be able to take the data that we have from all our sensors and move that up the semantic chain and do really sophisticated, complicated processing. I think right now, if you look at self-driving cars, Uber, Lyft, all those, Tesla, the sensors are decent. They need improvement, for sure, but not bad. The basic ability to find and track items are there, but figuring out, is someone really trying to cross the road or not? What do I do in this situation? All that really complex planning and prediction is that higher level semantic understanding is still really a bit of a challenge. But we need to be able to do that type of processing in distributed systems. And if you look at the Defense Department, they plan a system like the F-35. 15 years later, they might actually start building that system. So imagine what your iPhone looked like 10 years ago. And so you'd basically be using a 10-year-old iPhone in your brand new system. That's not great. Often, by that time, those parts are already obsolete. And trying to get those computers to talk to computers that are more modern is a real challenge. So how do we really raise up the level of computation and communication? Because we don't have a gigabit connection between platforms. Does anyone have an idea of what the standard communication bit rate is for most defense systems, comm systems are? What are the comms rates that you expect from your cell phones? What?
10 gigabit.
10 gigabit? You have a really fast cell phone.
That's 5G.
Well, I mean, we're lucky to get 50 to 200 kilobits consistently, and then if you're on your 4G modems, you can start to get faster, quite a bit faster speeds, hundreds of megs. But defense systems are lucky to have 200 kilobit, something on that order, maybe a megabit if you're really, really, really lucky. So with a typical camera sensor or a LiDAR sensor, or maybe 10 of them like most cars have, they're almost terabit data rates. LiDAR and other things like that, they're huge amounts of data. You cannot send that data between elements. You've got to process a lot locally. So how do we make sure we have those computational systems that have really rapidly advanced technology? When you're talking human robotic systems, the way that we operate, I could tell you, go down the hall, go into the elevator, up to your right is this. That's a whole bunch of semantic processing that often includes 6-dimensional or 8-dimensional degrees of freedom. So not just here I am in time, space, but I'm looking here, I'm looking here, I'm looking here. That processing, that semantic and visual processing is really pretty computationally intensive. And we're going to need all of that sort of semantic processing that I was talking about, because we can't just plug a high bandwidth connection into our head and see what someone else is seeing, although there are really fun technologies that let you sort of teleport and see some of those. But in a battle situation or in other situations, that's just distraction. You can't pay attention to that. No matter how much you'd like to watch a movie while you're driving, it doesn't work very well. Especially when you're getting shot at or there's really intense situations, you need to know exactly the type of information you need for that operation and nothing else. And you can't be distracted by it. So it's really important to work on the computation necessary to give the actionable information to people. And that's going to be really important for self-driving cars and connected systems all over. What is the right information to deliver to drivers and other people? All of this, as much computation as you can do, you still have to communicate something. And so we can call the FCC and complain, but the DOD can't always do that. There are lots of times where things can get jammed or you just don't have access. And for me, in the self-driving car future, when they're all connected and there's a lot of data moving back and forth, there's a story in Baltimore. There was like between 4 and 6 o'clock, like on Thursdays, I think, the airport basically had to shut down, and because their GPS signals were being disrupted and jammed, and so it was hard for planes to land and everything. So they couldn't figure it out, and it turned out that there was a delivery driver who didn't want his boss tracking him, so he bought like a $40 GPS jammer and put it in his truck, and every time he went to the airport, he was shutting down the airport, right? So that just tells you that, GPS, right? Everyone knows what's GPS? Who wants to? Global. So it uses a bunch of satellites and a really precise reference, and yeah.
So that product is legal?
No, but you can buy it, really easily from wherever you want. Actually, you can, for $20, you can buy these little software-defined radios that can do encrypted links or make any sort of comm you want. And for pretty cheap, you can buy a reasonably powerful amplifier to jam. So what I would not like is, traffic jams and auto accidents just because someone sets up a jammer by the side of the road and or does other interference, or even worse, at a big sporting event or venue, someone can come up and plant a dirty bomb or do something else and jam their frequencies and jam first responders from being able to attend. That would be bad. I met with Department of Transportation in Texas, and they've got billboard systems that display traffic information. They've got these metering for freeways to sort of make the traffic more moderate. They've got wrong way driver detection systems to prevent people from 3 in the morning, 2 in the morning, driving the wrong way on the freeway. They also hand out these transponders to large semi-trucks to alert them of other trucks braking or congestion ahead or areas to clear from. And all of those have been hacked, like porn put up on the billboards, and people can buy these little things to make the meter let them get on the freeway when they want. And imagine someone being able to have defects or false alerts or don't brake, to a semi-truck. Horrific accident that just happened recently, right, where a semi-truck barges into other. You want those systems to work, and you'd want them to be free of defects and vulnerabilities. So it's really important. How do we also, for our 5G networks, make sure that we can persist even when someone does jam? And in order to do that space-time adaptive processing, it requires trillions of operations per second. There's an example of a program that I did called the DARPA CLASS, Computational Leverage Against Surveillance Systems. And this took 10 mobiles, 10 people that can move around, and allowed it to do coherent multi-input, multi-output transmission. And does that make sense to anyone here and understands what that is? So effectively, you're coherently transmitting from every mobile such that in a multipath environment, meaning bouncing off buildings and streets and walls, as you're moving, all of that data coheres perfectly back at a base. So that's quite a feat. You have to update it every 10 milliseconds or so, all the weights and coefficients to transmit such that it coheres perfectly. And even better is that you can do that under the cover of a 50 or 60 dB interferer. So let's say you have a really powerful transmission TV station. I can be transmitting at the noise floor if that transmitter wasn't there, under this cover, so good luck anyone else trying to find you. And if they did, they'd have to do lots and lots of computation in order to do that, because we don't use a beacon, and we use these large sort of coded signals to sound the channel. You send out a bunch of coded waveforms back at the base station. They do massive correlators to find exactly when all the bounces and multipaths came together. And even better, you can completely null that large interferer from your receive system if you have multiple antennas. So you do a QR decomposition. It's a matrix transformation that whitens the channel. So all the center diagonal elements of the matrix that are strong, you can just null those out, and your noise, so you didn't get nulled out. So now I can do spatial and spectral reuse. So instead of having to designate this little bit of the spectrum for my use, and if anyone else jams, it jams my signal, I can actually cooperate with large interferers and small interferers, and that's a big deal for spatial spectral reuse. But that computation took about 2 trillion operations per second. And again, you'd be a room full of computers this big, or if you use an FPGA, field programmable gate array, it'd be about 7 of them, and several kilowatts of power, kind of a little hot for the side of your head. But we did it with an ASIC, with a 1600 core systolic array ASIC as part of a system on a chip for about 2 trillion operations per second per watt. So about a little under a watt of power dissipation. So we need to have that type of processing and technology in all of our defense systems. And I'm hopeful for 5G in our in our future 5G systems so that you can operate and our cars can drive on the road without someone setting up a jammer and sort of stopping us from getting the vital data. Because it's one thing to get your Netflix, Game of Thrones, or whatever, HBO interrupted while you're watching it. That'd be upsetting. But if you are relying on telematics and other data in real time for life and safety, you do not want to be interrupted. So it's pretty critical. And then what we also have to remember is that this is global tech and infrastructure. And for a long time, the US was really dominant. We had the best technology and a lot of leadership in that area. And now it's everywhere. And in fact, when we go off and fight wars or whatever we're doing, we can't always build and bring our own communication systems. We'll have to leverage what's there and or leverage the best technology from where it is. So any questions right now? I got off my first slide. That's an impressive feat. So in terms of what's happening now, the US has some pretty strong capabilities. We have Apple and Qualcomm. These fabless semiconductor industries are pretty good. They dominate the profit. At least Apple rakes in most of the profit in a lot of this area. But our hardware startups are really falling behind our foreigners. In the US, who wants to guess how many hardware startups around ASICs have been in the last 10 years minus this year? This year's been growth. Any guess how many hardware, A-round venture capital startups in hardware? 10. It's pretty close. It was a little under that, right? This year there have been many, I think as many as 10 in this year, not quite that many. But in China, about 1,000 of them in 2017 alone. It's a pretty dramatic difference. Like why? The question is why? And part of it is you can fund 100 software startups for one hardware startup. And so VCs would much rather take a bunch of bets on software startups than one bet on a hardware startup. But the other is the ecosystems that are available over there. Like whole cities will get access to EDA and IP and foundries and all of that. That whole ecosystem is available to them. And our integrated device manufacturers are a little bit at risk. IBM used to have a foundry, and they actually gave $1.4 billion to global foundries to take these foundries off their hands and have them run it for them. So that's it was hard for them to be an IDM. We have Intel Corporation, which is one of the last big integrated device manufacturers for CMOS technology, and they're doing okay. They're struggling a little bit to yield their devices and threatened a little bit from what's happening in China. And our R&D from our top universities migrates to Europe and Asia. So how many of you have used processes from TSMC? A few of you. How about global foundries? 1, 2 of you. Intel? 0. So that's interesting. TSMC gives about $200 million a year free silicon to universities. Berkeley and Stanford came to me and said, I need $300 or $400 million to build a clean room because I have to go to IMEC in Europe or this university in China that'll give me free integration of my new memory processes on 32 nanometer SOI for free. But that's like a direct transfer of our best technology into someone else's ecosystem. And so that's a threat. Now what could happen? At the same time, China is investing $150 billion in foundries. They're going to build 32 foundries, about $160 billion in fabless semiconductor company startups. In the memory market, in a $70 billion market, they're investing $50 billion, building 3 new foundries, and will cover their losses for 5 to 10 years in the marketplace. In quantum, another $20 billion. In AI technologies, another $25 billion. It just keeps going on. Huge, huge investments. So does someone want to guess what is the typical investment, R&D investment budget in the US? Like a US company, a big US company. How many billions do they spend every year in R&D? $250 million? Well, Intel is like one of the largest, and they spend $14 billion, so it's non-trivial a year in R&D, but really that's a lot of D. they're developing a lot of their processes. The really research and part is very small, probably closer to that mark. So when you look at that amount of money being spent by China and others and compare it to what we're doing, we're really not keeping pace at all in the US, including our industrial partners. And when you have that with joint ventures and acquisitions and deals that say, look, if you want to sell here, you've got to build here and you've got to tell us how to build it, it's a potential threat to our leadership. And if we don't have production here and we invest a lot in R&D and a new device here, but we can't make it here, it's also a risk to our future. So what could happen? In Asia, you could have 32 new foundries. 7 of them are better than 32, less than 14 nanometers. The trade policies and acquisition and startup culture really shifts all of the production and supply to Asia. And that could be okay, except if you're an Apple or a Qualcomm or others, and China might say, look, you know, you've been used to be getting first choice Apple in terms of chips, but you know, Huawei, I think we're going to let go ahead of you. Or if there's a little conflict and they just decide to turn off the spigot, and those parts that we depend on for defense or for our 5G network or et cetera are now just cut off. Or even better, imagine, so in China right now they have a great firewall. Effectively, they monitor what goes in and out and can shut off, and they keep our big internet giants out of their ecosystem for the most part. And what that has done is made Baidu and Alibaba and others really amazingly profitable, powerful companies that have gone from the cyber realm to the cyber physical. They take their massive profits and they're going into automated manufacturing and self-driving cars and using those profits to become leaders now in a lot of other industries. And like, so who is probably, you know, when do you think of when you think of electric cars? Who's the leader in that? Tesla, right? You know, but they pale in comparison to the number of electric vehicles being built every year, right? There's a number of firms in China that produce many, many more cars than Tesla does. So they have a real chance of having dominance. And so what could happen is that our fabless semiconductor companies will, in order to China has their own problem, right? They import 80% of the microelectronics that go into the things they sell us, and they're dependent upon us, so that's a problem. They want to switch that around. They want to produce 80% of the parts, the microelectronics that go into the things that they sell us. So they're smart in wanting to do this. But what could happen is once that dependence and collaboration is no longer, they could cut us off from that supply. And worse, the new technology that we develop and invent won't necessarily be benefited by us. The IDMs like Intel and others might have a little bit of trouble, especially once China has the ability to build their own CPUs that compete with Intel processors. And this overproduction could cause our current foundry ecosystem in the US, which is kind of fragile, to sort of disappear. And you look at global foundries, it's a third-rate foundry provider, but fairly big. They just sold their Singapore plant. They just sold a plant in East Fishkill in New York. And they've invested maybe $20 billion, the United Arab Emirates. And they're probably worth $5 billion at the moment. So if you're an investor, it's probably not a really good business for them to invest in. And so hopefully they'll be around for a long time and be profitable, but it's a tough business. So those foundries, when there's a lot of overproduction and supply, could be at real risk. And then the best R&D won't just be, escaping the US, it's going to be from Asia. And actually, if you look at it now, the number of publications and the quality of the students and everything is pretty incredible. The growth rates in patents, the growth rate in publication is by far coming from Asia, and especially China. So what have we done in the past? Japan took a big hit at the semiconductor industry in the 70s and 80s. TSMC was created by Taiwan. They basically invested, instead of defense, they invested in semiconductors. TSMC makes more money after taxes than before taxes. So tells you how important semiconductors are to some nations versus us. But the US was worried, like really worried. And so the Office of Secretary of Defense actually invested about $900 million at that time in this VISC program, which is a couple $2 billion in today's money, which created EDA tools, basically allowed, instead of hand wiring a couple thousand circuits, you can now create the 12 billion transistor type circuits we have today by creating that whole EDA ecosystem, design ecosystem. It's really powerful. It kind of changed the digital revolution that we have today. The MIMIC program, microwave machine integrated circuits and others, millimeter wave MIMIC, did gallium arsenide technology and revolutionized our ability to do SATCOM and mobile comm. So big, big investments that I think really changed the industry. And then as we saw Moore's Law continuing to go along, we did a public-private partnership with industry to keep that advancing, to keep moving down that technology scaling. And so those were all big investments. And they were relatively effective. I think so effective that the US government basically said, okay, that's a successful industry. They don't need help. You know, Silicon Valley, they don't need our help. It's good. But China's been planning for a while. And they're smart people. And they are able to invest resources and have a commitment to their strategies. And they're coming right when Moore's Law is approaching that sort of end of its. Moore's Law is about a technology, but it's also about economics. The cost to keep scaling has just gone so high that it's slowing. And so if you're a late follower, you can just kind of catch up really quickly by benefiting from everyone else's past work. And that's what they're hoping to do. And they could. So I hope that we need and now have to have a strategy that reacts. We could just let this happen, and frankly, all of you will be fine, and I'll be fine. We just might have to go somewhere else to do really advanced technology. Right? Maybe we can design anywhere, but it's not going to be made here. But I think in order to have a good future, economically, our self-driving cars, a lot of other systems really depend on our ability to have advanced microelectronics and systems in them. And I think the US needs to have that opportunity.
Question.
Yep.
So what was the last purple bar? The last bar.
So that is, what do we do? What does the US do? We've spent billions before. What do we have to do now? And the cost has gone way up. A typical foundry is about $20 billion to make. How do we match those investments? So the DOD sees a number of issues. One is how do we get access to foundries for building our custom ASICs to have that real advantage that I talked about. The second is a lot of consumer off-the-shelf parts, FPGAs and controllers and CPUs, are in our defense systems. In fact, most of the things that we buy are those types. How do we make sure that there aren't problems with them? You saw the Bloomberg article. Anyone saw that article that showed that suspected that little chips could be put into boards that could allow interference? There's an Intel problem with a side channel and other attacks, et cetera. Vulnerabilities in your systems. We want to make sure that the things that are guiding missiles and defense are not vulnerable in that way. And then the biggest problem is how do we have an industrial base that supports all this in the US? It's a challenge. One that supports all the new ideas from people like you, allow them to be focused and transitioned into production and state of the art, state of the practice, and in legacy and boutique things, specialized gallium nitride or whatever else, optoelectronics. And so we've invested in a number of programs, and this MINSEC is designed to start to address the middle and a little bit of the bottom part of the problem. So what do we need to do? We need to revise the way that we do trust and assurance. And Congress defines trust as the confidence that the system would behave as intended, free of defects and vulnerabilities over the life cycle of the system. I call assurance the things that you do to instill that confidence. It's going to do what it's supposed to do and not something else. Right now, that trust has been done with guns, guards, gates, and background checks and US citizens only. And when you have 5 or 10 billion transistors in a circuit and you bought most of the IP from someone else, that's not going to do much. A human can't look at that and make sense of it, right? You have to have a different way of doing assurance and trust. We have to have a very good ability to do validation and verification. Really, really important, especially when things are that complex. How do we enhance that, enhance industry to do that? We still have to deal with this government unique needs, this problem of designing something and then 10 years later building it and already being obsolete. How do we advance it very quickly? How do we make really specialized gallium nitride and high power devices for the government? Really importantly, and very thankful for the university for creating so many bright, talented people interested in this field. But the workforce in the US is probably one of the major reasons why it's hard for major foundries and tech companies to site here. It's hard for them to find the adequate workforce. And they can get it for cheap and really well-educated people in Asia and other places. It's a challenge for them. And we got to do something there. The R&D to lead the future, as Moore's law is starting to slow. Page 3 of Moore's seminal paper. I don't know, has anyone read Moore's seminal paper? Anyways, on page 3, he talks about predicting that eventually you can't make things smaller. We're down to a few nanometers and hundreds or tens of atom widths, right? You start going smaller and things start not working well. And it's very expensive. He predicted a lot of those things and he said, well, we're going to have to figure out new technologies, not just scaling. We're going to also have to change the way we do architectures and design, because when you start having so many circuits, it's so complicated to design. So that's what we're investing about $300 million a year through DARPA on the ERI, Electronic Resurgence Initiative, and to create those new transistors, to do new computer architectures, and to do new design techniques. So you don't have to have a team of 1,000 people doing designs, maybe teams of tens or less, being able to do really sophisticated designs. The DOD needs to do modernization, so we need to be able to get into the business of capturing the types of technologies that you can buy here into our DOD systems and not having them being 10 years old. And then last is this access, availability, assurance to state-of-the-art production in the US. And how do we convince Intel to build their next foundry here versus Ireland? Samsung to build their next foundry here versus Vietnam? Convince TSMC to decide to come over and build a foundry here? Ask global foundries to keep in the game? Those would be really good things for us to do. Yep.
On this legacy issue, how much do companies like SpaceX or even Boeing and so forth have with that? Or is that kind of more unique to the defense space? Because
some space have a problem with that. But Boeing, if they do things for the government, they have a little bit of a challenge for it. Usually it's the Northrop Grummons and Lockheeds and others. SpaceX is like fast and loose. They just do whatever they can to make it work. And they're not worrying as much about rad-hard and reliability right now, partly because they aren't up there very long. Eventually, they're going to have to worry about it, and if they need a lot more computation, it will be a challenge for them. So I want them to care more. Right now, people like SpaceX they're literally just, if you look inside the box, it's a little scary, but they're doing amazing things. Yeah.
So you attribute to the current state of affairs to lacking qualified workforce.
That's one of the attributes, yeah.
Okay. Was that also the reason for, because it's a process, right? I think the decline in microelectronics production, manufacturing capabilities, this happened over a period of time. What was the trigger, or was there no trigger, just?
I blame Motorola. And there's many other people to blame. But in particular, they had a advanced HDMI, it's a high density integration, HDI packaging technology. and they had it in Texas, and the workforce was a little expensive, and they could get it cheaper in China, so they moved it to China, and the Chinese manufacturers said, that's great, but you have to give us the process because we need to be able to sell it to other people. And in about 3 years, they completely shut down all their US operations, and then packaging is now almost exclusively an Asian Chinese process now, right? That's what happened. And continually, the desire to have cheaper costs. I mean, microelectronics is a horrible business, extremely competitive, and microcents make a difference oftentimes. So the desire to, and this was 10, 15 years ago that I said, well, look, technology will follow production. When the production goes over there, the technology and the ecosystem will follow. And it's a real problem and concern. And I think, it was fine because a little here, a little there, and we're still making good money as an integrator, and the Apples are doing okay, and Qualcomm and others. But I think people just didn't recognize that the ecosystem had eroded so much in the US. And then when, are you going to get a job and study semiconductor manufacturing at Michigan? You've got a clean room here. It's pretty good for university. But how many jobs are there in the US compared to in Asia in that field? Not good. And the number of computer science students you have compared to the number of circuit design students is pretty remarkably different, right? And why not? If I can, make $90,000 or $110,000 working for Google or someone else in software, or I can go get an advanced degree and have a lot of debt, 50 grand a year in debt or whatever it is, what would I choose? I'd probably go into software. Not me, but most people would. So it's a real problem. Go ahead.
Yeah, following on that, what is the DOD looking for to solve any of the push the workforce? Because I'm a younger student, right? And very few of my colleagues are, American, right? I'm looking at it, and yet down the road, it just seems to be getting worse, right? What is the DOD doing to try to?
So part of this, $3.5 billion that I was able to get, a portion of it was for workforce development. Not a lot, because I asked for 6, I got 3, so you can do what you can. So 10, 20 million a year is what starting in this year for workforce development, which includes, I'm hoping, 80 or 100 scholarships for this area. I think something even more radical needs to happen, though. If we want a TSMC or someone else to come here and they can't get the workforce they need, and literally they put out their hiring notices and can't find people, let's let them import 60-some% of their workforce, the best people they can find, fast-track citizenship, and ask them and the company, and maybe even some sharing from the employees, to take some fraction of their salary for the first 5 years and pay for a US citizen to get an education in that degree area. That would be pretty powerful. So I think some combination of those things, some rational immigration reform, some incentives that would really promote having the best people come here and stay here and work here and train the next generation.
And
So,
what about just DOD putting lots of money in educating people in science and technology
so I mean,
in America?
I think 300 million a year bump is decent. It's not huge, but it's a good bump. And that's going to go to novel devices, materials, circuits, and architecture. So even though it is going through DARPA, and DARPA gives most of their money to the primes and others, it does go a lot to universities, and that will help. What I'm encouraging them to do is every major contract that is going to be funded through this activity is to have 1 or 2 fellowships or scholarships just as part of any major contract. And what I would like eventually is every acquisition program within the department also have significant investment in education and workforce. I'll talk a little bit, if I have any time, because I've gone really slow, about how else we think we can have that encouragement. So what does the department can do? We can do policy. We can change our export controls. We have the strategy and directives, the national strategy that we can influence, which is good. We have a ability to do some sort of captive foundry capabilities and give access to runs. A number of you, maybe in the past, if you've done designs, have got access to foundries through TAPO, Trusted Access Program Office, through DARPA and others to get access to multi-project wafer runs. This Trust and Assured Microelectronics program is designed to make sure that when we buy things, we can validate them, we can make sure that they're working the way they are, and promote standards in the industry to help with that assurance. Because we can't check everything ourselves, we have to have industry value assurance. The DOD MINSEC program is $300 million for DARPA, modernization, and then spending a little money on our rad-hard and specialty needs for nuclear and space modernization. This part is unfunded so far for the most part. How do we make sure that there are multiple commercial foundries in the US? What incentives are going to be needed? And luckily, it's an interagency problem. So we've got Department of Commerce, Department of State, Department of Treasury, Department of Defense, Department of Energy, National Nuclear Security Agency, all thinking about what are the proper incentives to make those foundries choose to build here. And when we talk about building a system, we talk about having great people have innovative ideas. That's not enough. They need to be able to build something and put it in the hands of adopters and provers. So all along the way, as you go through this, there are opportunities for people to alter it, to escape, steal data, to inject malicious things. We need to have the ability to understand all the threats, the confidentiality, the integrity of it, and the availability of those parts. What are the impact of the systems that I'm building? So if I have a car, cars have like 200 or 300 separate ECUs, processors in them all connected together. How do I know if I have a fault over here? Is it going to affect things over there? How do we know the impact? How can we mitigate those? What are the efficacy of those mitigations? What's going to cost me to try to protect against those? And I need to be able to communicate that very clearly in every stage of the design and tell people how to protect their systems. And ultimately, at the end, I need some beautiful integral that is a combination of all those threats and mitigations to say, my system is this safe. I have this much confidence that when I get in that self-driving car, it's going to do what it's supposed to do and not drive me, off a cliff or into a barrier. And I think that standard has to be delivered into industry and adopted. If you want to drive on a road in Texas, big trucking and industry, there has to be this level of assurance of electronics and the parts that go into it. If you want to be part of our 5G communications network, which could be really critical for first responders and everything else, we have to have this confidence that it's not just going to be shut off or interfered or jammed. So I think that's going to be a really, really critical component to incentivizing the production. Congress asked us to, I'm not going to read all this, but to develop a strategy to address it. And they basically asked, tell me what you need, your ConOps, your capabilities. Tell me how critical they are. Like, is this a really important thing or is this not an important thing? Map the microelectronics that you have into delivering those capabilities. Is this processor really critical to doing this function, or is this ASIC really critical or not? And then from that, tell me how to get an assured access to it. That can get those parts, that they're going to behave as they intended. I have confidence in them. What do I do as a designer to protect that intellectual property and that production? What am I going to ask a manufacturer to do to protect it? Such that I can get all the different types of parts, consumer parts, ASIC parts, captive parts. The department uses a lot of different things, memories, power electronics, GPUs. Unfortunately, ASICs are about 3%. We spend about $1.4 billion at mil-aero, $5.8 billion total microelectronics, the DOD, 1.4 mil-aero. 3% of that are ASICs. It's bad. It's really small. It's 100 million a year. For the microelectronics industry, Intel or Global, they're like, don't even bother us with that. This is just not enough. I don't care. You're bothering me. Go away. So we've got to make sure that we can get all those things that we need. And make sure we can ask ourselves these questions. Is the confidentiality of this part critical? Can I protect it myself? Is the integrity critical, meaning will it work, and is it important that it works, and can I protect it myself? If not, do I have to ask the manufacturers to protect it? Do I need to use a trusted flow with guns and guards and gates and only people I can have? Or can I protect it myself and use a more commercial flow to get all the parts that I need? And we're really trying to promote the adoption of processes that will shift from, humans are amazing. We've got these prefrontal cortexes that can think about and understand what someone else might be thinking and develop a model of the world around us and watch each other and all that kind of good stuff. But that breaks down when you have to try to understand what 2, 3, 5, 10 billion transistors on a circuit are doing, or complicated processes. And humans just can't do that anymore. We used to, yeah, you're okay, come on, you can work over here. And then the internet came along, we realized that the whole world could connect to us if we have the internet connected, so we have to have a firewall. And then, the software we're running has vulnerabilities. We can't trust it really, we have to protect it there. And it turns out, the hardware isn't that trustworthy either. Don't pick up that USB drive and stick it in. And then lastly, I actually don't trust the people fully. So how do we move from that model of guns and guards and gates to and US citizens and background checks to a way that we can have a lot of sensors and data about the world? As I'm designing a circuit and a chip, there's a whole bunch of detailed information that's captured by the computer systems in their design. As I'm in a foundry, in a modern foundry, they're fully automated. They've got wafer shuttles and robots that move these things around at very high speeds. No one touches the wafers. They're literally fully automated in their processing. There's cameras and sensors everywhere. Could I take all that data about what I'm making in the design process and the foundry process, take a record of that data in a cryptographic, blockchain-like employment, so that every step of the way, I record what happened to it, and if enough of the activity in that area is recorded and something goes wrong, you could trace back what happened. That's a big deterrent for someone trying to intentionally create a defect, to intentionally be malicious insertion. And wouldn't it be nice if you could use all of this, not only about the processes and IP, where it all came from and who designed it and all that, but supply chain data. How vulnerable is your supply chain? Is it, if I have a natural disaster, what's likely to happen for my ability to produce this part? And could we do an integral or some value and policy that valued the assurance, that valued the security and performance of these parts, and allowed it so that if you want to sell into the US market, you have to have this provenance, traceability, observability of your IP, showing us that there aren't intentional defects, that it's going to be good for the self-driving car application or our 5G network, and have a quantifiable risk-based approach to promoting that as a value. And in SWaP-C, does anyone know what SWaP-C is? Size, weight, power, cost. Those are the things that you optimize for any system. I want SWaP-C to mean size, weight, assurance. Assurance that it'll perform the functions that you want it to do. Assurance that your supply chain will be there. Assurance that it's superior technology. And have that valued by acquisition professionals and by others in other industries as part of the equation. And have it as easy to find 1,000 reviews about a particular shoe, like on Amazon, as it is as easy to find reviews about the electronics that are in these systems, our defense systems, as it is to find about consumer products. So I think I'll stop there. I probably overwhelmed you. Any questions or thoughts? This is the strategy that we've developed. The base of innovation, disruptive R&D by DARPA, proactive awareness and security to know the entire global supply chain, make sure we understand it, working with our allies, having incentives and market growth to attract foundries to be here, enhancing our state of the practice and other manufacturing, and then providing access and assurance to deliver all these things that we know are going to be important for the economic growth, but we're also going to need for our defense systems. And then creating environments where we can have supercomputer systems and emulators, really large access to EDA tools. Sorry, there's a typo there, I noticed. Software and validation capabilities, experts that really know how to build these systems on chip. People from the end use environment, persistent people from government, and then the best ideas and innovators from industry and academia to be able to work in these virtual environments collaboratively to build large-scale projects, large-scale systems on chip, and have access to the state-of-the-art, state-of-the-practice production capabilities and packaging, and funding to do prototyping to deliver real capabilities, things that fly, things that sense, self-driving cars, drones, and other things around microelectronics in the DOD. And as DARPA does their new tools, materials, designs, and architectures, making sure that they land in a domestic ecosystem and can be produced. So I'll stop there. Thank you.